Walaikum Assalam, sir.
Okay, I have a problem here in my apartment, okay, because some people are working somewhere, probably they will be creating noise, okay. So we have to, what do you call, bear it.
Yes, sir.
So can you tell me where we were in the last class?
Sir, we had solved the example 3.19.
Probably we have discussed about, okay, let me share it out. Actually, we are living in a very strange place, okay, the country, okay, the people do not care about the well-being of others. For this reason, okay, everywhere is indiscipline, everywhere, starting from school, colleges to personal life. Just hold for a second, please. I have to receive. Okay, can you see this slide?
Yes, sir.
So probably we have also discussed about this issue in the last class, okay? That means if we have an impulse in the time domain, okay, we are dealing with discrete time system. So because we need to know this thing, the reason is that in all discrete time signal, you have already learned that can be expressed as a weighted sum of impulses. For this reason, if we know the Fourier transform of an impulse, that result can be utilized in finding the Fourier transform of some other representative functions. So as you know that by using the shifting property of Fourier transform, okay, if we have a function something like this, a very localized function at the origin, then its Fourier, by according with the definition of Fourier transform, this is what the Fourier transform equation of our function. Now, by using the shifting property of your impulse function, this is equal to the value of this function at n equal to 0 at the location of your delta. It is simply equal to e to the power j omega dot 0 is equal to 1. Now, you can easily see that if we have a function that is impulse localized at the origin, its Fourier transform becomes constant, okay, with amplitude equal to 1. This is what the Fourier transform. That means your impulse contains all the frequencies from minus infinity to infinity. That's why when we are investigating a linear system, we usually refer to the impulse response. From impulse response, we can calculate the frequency response or transfer function. And by investigating the transfer function, the performance of your linear system can be investigated in the frequency domain that already you have with you in your control system. But sometimes you see that your impulse can be shifted. If your impulse is shifted to a location, say here, say this impulse is delta n minus say n0. Did you discuss it in the last class? Then what will be the Fourier transform? It will be equal to sum n equals minus infinity to infinity delta n minus n0 e to the power j capital N, something like this, minus. Then what is the value? This is what the value of this function at n equal to n0. So this will be equal to minus j capital omega n0. This is what the Fourier transform. So from this result, what we can infer, okay, that if we shift the impulse, then our Fourier transform of delta n was equal to 1. When we shift it to a location n minus n0, then it will be equal to 1 multiplied by e to the power minus j omega n0. If your n0 is in the right, then it will be this. If it will be in the left, negative, then it will be e to the power plus j omega 0 n. This is very important result. Although the magnitude of your Fourier transform will be same, this is ft, Fourier transform of delta. But a phase shift will be there in the Fourier transform. That will depend on the how many samples it has been shifted in the time domain. Okay, along with this shift in the time domain, something we may have some other properties that we will discuss later. Okay. Now another inverse problem. Okay, that means a localized signal in the time domain will be generating a continuous signal in the frequency domain. And again, we can have another perspective that if we have a localized function in the frequency domain, what will be the corresponding function in the time domain? Because in many of the cases, duality property is needed to take inverse transform. Okay, in this this example actually illustrates this, that we have a Fourier transform of this form. So you see that Fourier transform is represented in this way in the frequency domain, and it is periodically appearing in the frequency domain that can easily be expressed in this form. Now, if we want to find the corresponding signal in the time domain, what you need to do, we have to evaluate that integral over one period of your xj omega. We know that in one period of your xj omega, we have a delta at n equal to omega equal to 0. So this is what that inverse equation for xn. And like using the same shifting property in the frequency domain, this result will be equal to what? Value of this function at omega equal to 0. It will be equal to e to the power j 0 dot n is equal to 1. This integral, okay? But as a scaling factor is there 1 by twice pi, so 1 by twice pi will be there. So this result is actually the Fourier transform. This result will be equal to 1 by twice pi. So if we have a signal and this is equal to xn, a discrete signal, so your signal will have an amplitude equal to 1 by twice pi, and it is appearing for all values of n, starting from n equal to minus infinity to infinity. This is what that corresponding signal for this Fourier transform. So you can easily see that if we have a localized, for example, Fourier function, then the corresponding signal will not be localized in the time domain. So this result we will be using later in order to find what? In order to find the Fourier inverse. For example, if your signal is shifted in the frequency domain, how it will be behaving in the time domain, that we will also discuss later. So this equation will be needed to take Fourier inverse, but at this point, okay, we will be switching to our continuous time. Before going there, let me tell about something, that how can we utilize this property to take the Fourier transform of some representative function. For example, in your book, you have some problems there, practice problem, you can solve them to get accustomed to it, how they can be used to find the Fourier inverse. Okay, for example, say in your problem 3.13, the other problem you please solve. Okay, if we have our xj omega, e to the power xj omega is equal to 2 into cosine 2 omega. And you see that your capital omega is continuous. So this is the Fourier transform of a function or a time domain signal. We do not know yet unless we take the inverse. But here in this case, you see that whenever you are having this term, it signifies that your signal is discrete time. So your discrete time signal is there, and corresponding Fourier transform is continuous in capital omega, and it is periodic. You can easily see that this is periodic. Now, if you want to find the corresponding time domain signal, what you need to do, you have to take the Fourier inverse. Then your xn would be equal to 1 by twice pi, and you have to integrate between pi to pi. This is your x e to the power j omega and e to the power j omega n d omega. This is what your synthesis equation. Either you can use this equation, or we can use our previously obtained result to find the time domain signal easily by comparing. Okay, what we have seen, if we have delta n, the corresponding ft equal to 1. And if we shift our delta n minus to a location n0, the corresponding ft will be equal to 1 into e to the power minus j omega n 0. So by using this result, we can easily find the Fourier transform, Fourier inverse of this equation. Okay. In order to do that, what you need to do, you have to express this equation into exponential form by using Euler identity. Then your 2 cosine 2 omega equal to what? It is equal to, because you know that your cosine omega 0 equal to what? E to the power j minus j omega plus e to the power j omega divided by 2, isn't it? For cosine, 2 omega is there, 2. Then, okay, we have a 2 there, the 2 is there, okay. So this is equal to e to the power minus j 2 omega plus e to the power j 2 omega. Okay, that this is what a part of your signal, this is another part of your signal. You can take your Fourier inverse in for the individual part. What is the Fourier inverse of the first term? Hey, are you there listening or simply sleeping?
Yes, sir.
Then what is the Fourier inverse of the first term? By comparing with this result? Okay, do it by your own. So the rest of the problems are there. You try to look at your problem. I don't know, with this minimum engagement, how will you learn? Okay, now we are switching to our second category of our aperiodic signal, that is what continuous time. These two equations are the Fourier transform pairs. If we have a signal xt that is not periodic and it is integrable, that means your signal has energy that is finite, then what you can do, we can transfer the signal in this way to convert it into frequency domain. This equation we have already learned at the beginning of the chapter, where we have shown that if we have an LTI system, then our input is a complex exponential, then our output will also be a complex exponential, and they will be related by a factor, we call it transfer function or frequency response. And we define the frequency response at the time that Hj omega is equal to integration of minus infinity to infinity H tau into the power minus j omega tau tau d tau. Okay, this tau is your what we call dummy variable. That's the response. So in our Fourier transform pairs of discrete time and continuous time, we have seen that in the case of discrete time signal, the Fourier transform is actually continuous in capital omega, and we need to, and they are periodic, and we need to know our Fourier transform from minus pi to pi in one period to get our time domain signal back by using inverse integral. But this is not true for continuous time. In a continuous time case, you have to span the whole frequency range to get your signal back, theoretically from minus infinity to infinity. And again, what we have learned in our Fourier series, that in the exponential form of Fourier series, your frequency or the harmonic number ranges from k equal minus infinity to infinity. The reason is that if we do not include the minus value of k, then conjugate coefficient cannot be generated and your signal cannot be real. The same reasoning is true in this case also. If your signal xt is real quantities, then is that we have learned earlier. And later we'll show using some example that your xj omega for a real signal xt will be an even function of omega. That means it will have a part in the negative frequency and it will have a part in the positive frequency, okay? Otherwise, a real signal cannot be generated. Negative frequency has no meaning physically, but they are appearing in our calculation mathematically because of the complex exponentials. But we can also transfer this equation into two parts. You will see that we can split this equation into two parts. One part is called cosine transform, another part can be thought as sine transform. As you know that our signal e to the power j omega t can be written as cosine omega t plus j sine omega t. Then if we put this thing there in this equation, then you see that your xj omega would be equal to integration from minus infinity to infinity xt into cosine omega t dt plus j minus infinity to infinity xt sine omega t dt, okay? This can be thought as a real part of your xj omega, and this is the imaginary part of your xj omega, okay? In either ways we can go. Let us illustrate the thing by using a simple example. And these equations are continuous. Your omega will be, xj omega will be complex, and it will be what you call a continuous function of omega. And in order to reconstruct the signal from transform, we need to integrate this equation from minus infinity to infinity in frequency. Okay, this is so in this example, we have a signal there, xt equal to e to the power at ut. Is it periodic or aperiodic? Are you there?
Yes, sir.
I have asked you a question. Can you speak? Is your signal periodic?
No, sir.
What is the shape of your signal?
Sir, an exponential decaying signal.
Exponentially decaying signal starts from?
Sir, it will start from the y-axis with a value of that's given in the exponential. And
No, in time it starts from where and ending at where?
From 0 to infinity.
0 to infinity.
That means it is simple and exponential signal decaying exponentially from 0 to
infinity.
Maximum value equal to 1 at time t equal to 0. So this is an ideal example of an aperiodic signal. And it is a square, it is integratable because within this integration, if your a value is positive, then that integration will have finite. But if you have your a value that is negative, then your signal will be unstable. So we are not going to the unstable region. We are assuming that our a is greater than 0. If your a is greater than 0, e to the power minus at will be a decreasing function of t. And if we want to take the Fourier transform of this function, we apply the signal into the integration of Fourier transform. Here, this is your xt. Then anybody can integrate it. Okay, this is how your integration. You can easily see that your xj omega is complex. It has a real part and an imaginary part. Okay, can you find the magnitude of xj omega? Magnitude of xj omega equal to what? 1 divided by square root of a square plus omega square. And the angle of xj omega equal to? What is the angle? Minus tan inverse omega divided by a. Okay, I have actually examined your MIDI script, but surprisingly have seen that except few students, okay, those who are actually good, the others are simply just passing their time, because this time you could not copy. For this reason, your result is awfully bad. And this actually almost coincide with what we have seen in the physical exam. Okay, some simple mathematical thing that a high school student know, you have the problem with them. You do not still know, many of you, how to differentiate between a current source and a voltage source. You still do not know how to write Kirchhoff's equations, something like this. And few things I have observed that when I give the exam, you explode where internet, okay, or other issues, something like this. This is not that simple, okay? Try to engage, otherwise you will suffer from the consequences of this, what we call inactiveness. Be careful about that. So this is what the thing. Now tell me, your frequency ranges from minus infinity to infinity. If you want to plot this magnitude, how it will look like? What will be the maximum value and where it is occurring for the magnitude?
Sir, at omega equals 0.
At omega equal to 0, your magnitude is equal to 1 over a, isn't it?
Yes, sir.
And in either side, what will happen? If we go, for example, in either side with omega, you will see that your function magnitude is changing in this way, something like this, isn't it?
Yes, sir.
And it must be what? Periodic. So after twice pi again, no, it is not periodic, sorry, because it will be going to zero eventually. So our xj omega magnitude, by you can easily examine in this figure that it will be something like this, okay? It will be something like this. Now, if we have our xj omega, that means only the low frequency component of your xj omega is contributing to your transform, but high frequency terms will be attenuated, for example, very sharply with a lesser magnitude. As a result, if we can define a bandwidth with some criteria that you know, that you have known earlier in designing many of your electronic system, if you design really, then you know this thing, that we have some criteria of or selecting the frequency or bandwidth of a signal, because in the time domain, you will never be able to know what is the frequency content of this signal, because this is not periodic. In the case of periodic signal, at least you will be able to know the fundamental frequency and can say that all other frequencies will be the integer multiple of fundamental frequencies. But in this problem, can you do that? Because in this problem, you see that your signal has this form. If you have this signal of this form, then from this time domain signal, you will never be able to know what is the frequency content. But once we transfer it into frequency domain, then you will know the frequency behavior of your signal. Now the question is, if you want to use this signal in practice, we cannot go to minus infinity to infinity. You have your finite range of frequencies that can be handled by a real system. Then what you need to do, you have to use some criteria of selecting the usable frequency range or tractable frequency range. That we sometimes call bandwidth of our signal. That bandwidth can be determined by using some criteria, but one of the widely used criteria is what? 3 dB point. In your signal itself, your 3 dB point will be defined by the maximum amplitude times 0.707 or maximum amplitude times square root of 2. But in power spectrum or in a square of your signal, it will be equal to half. That sometimes the 3 dB point in dB, it is minus 3 dB in power. But in voltage and current, it is different, okay? So these 3 dB frequencies can be determined from the spectrum of xj omega or from the square of the spectrum of xj omega. Because square of the spectrum of xj omega will be related to power and energy that we will discuss later. But if you want to use xj omega only, then your half power point will correspond to the maximum value of your spectrum multiplied by
1 by root 2.
1 by root 2, exactly. So this will be your frequency A in this case, that the significant amount of energy of your signal will be contained within this bandwidth. So you can start with designing to process this signal by using this frequency information. Phase angle is also important. The reason is that unless you know the phase angle, you cannot really find the real shape of your signal. And as you have already known that your phase angle is minus tan inverse omega divided by A. So you will see that at omega equal to A, that means at the point of your 3 dB, your phase shift will be equal to what? In the positive range of frequency, phase shift will be equal to minus pi by 4, because tan inverse 1 equal to pi by 4. And in the negative range, it will be equal to plus pi by 4. As your frequency is increasing, your phase shift is increasing, but it will be saturated at what point? Because the maximum phase shift will occur, say if your omega is tending to infinity in either sides, then your phase shift will be approaching to pi by 2, okay? For positive region, it will be negative pi by 2, or for negative region, it will be positive pi by 2. Both your phase shift or phase angle of your xj omega and magnitudes are needed to reconstruct your signal. And you see that theoretically your frequency is ranging from minus infinity to plus infinity. Now let us discuss about another signal. Okay, can you identify this signal? What is the shape of your signal?
It's a pulse.
It is a pulse, okay, and centered at the origin, isn't it? That means it is a rectangular pulse with duration equal to
2T0.
2T0, okay? That means we have a pulse, something like this, okay? Minus T0 to T0, no value elsewhere. And it is aperiodic, certainly, isn't it?
Yes, sir.
Then if you want to find the Fourier transform, just simply put this function into your integral equation, integrate it from t equal to minus infinity to infinity. But we do not need to go to infinity. We do not have our value of our signal beyond minus T0 to T0. Then this is what your integration, isn't it? Magnitude equal to 1. If you have different magnitude, that magnitude will come here, okay? That will not change the characteristic shape of your transform. It will simply scale your transform to some extent, depending on that amplitude. In this case, your amplitude is equal to 1. So this equation is simply equal to what? This is equal to actually minus 1 divided by j omega into e to the power minus j omega t0 minus e to the power j omega t0, isn't it? Then you can use your Euler identity there easily to convert it into a sinusoidal a form of something like this, okay? At omega equal to 0, by using L'Hospital's rule, you can find what is the magnitude. So you see that the magnitude of your spectrum at omega equal to 0 is 2T0. But as your omega is changing from minus infinity to infinity, it will take the shape of a sinc function that we have discussed earlier, okay? This result will be very useful later when we will be taking our Fourier transform or inverse transform of some representative function. It is needed in many of our purposes, particularly in communication engineering. When we will be dealing with some application, it will be clear to you. Okay, this is what your nature of your signal in time and corresponding frequency. And you see that your signal is even in nature, in time, and that is giving you your Fourier transform that is real. No phase angle is involved there. Okay, so this is what your maximum value. It is actually 2T0. And we can easily find where your zeros are occurring, because we have a term there in the numerator, sine omega T0. So your T0s are occurring at what frequencies?
N pi, omega equal n pi.
Omega equal n pi. Okay. This is what your numerator, isn't it? Oh, sorry. This is your numerator, omega into T0. So your zeros will be occurring at where? When omega sine into omega T0 is equal to plus minus n pi, isn't it? Then your omega equal to what then? Omega is equal to, no, this is equal to not n pi. This will be equal to 0 when omega T0 is equal to plus minus n pi, isn't it? Where n is an integer. Do not just mix it with sample number, okay? In this case, it is an integer. You can put another integer there, no problem. So your angular frequency omega would be equal to what then? Plus minus that integer pi divided by T0. So your first zeros are occurring at where? Your first zeros are occurring at omega equal to pi by 2, pi by T0, and positive and negative, okay? Pi by T0. So as we don't have any for the physical meaning of our negative frequency, So our in terms of real frequency, it is pi by T0. Now you see that some interesting thing, although probably we have discussed earlier, but I am again reiterating it because the many implications. For example, okay, now you see that we have our zeros there. First zero, let us consider the first two zeros because this side main lobe has an area that is much more larger than the other lobes. For this reason, most of the energy of your signal will be contained within this lobe. So as a result, in order to, although your frequency is ranging from minus infinity to infinity, but we do not need in practice, okay? We can truncate the frequency into a finite value by examining the Fourier spectrum, okay? That cannot be judged from time domain. Another important issue is that your zeros are occurring in this way, okay? If we have our t that can be tunable, say, we are changing the value of t, then what will happen? If your t is larger, then what will happen? The width of your main lobe will be shorter. What does it mean? It means that the frequency spectrum will be squeezed. That means your bandwidth will be, requirement will be lesser. If your T0 is shorter, bandwidth requirement will be higher. For this reason, say, in 1 second, for example, say, we need to send, say, 8 bits. Say, these are the bits. If we want to send 8 bits per second, say, then we need a bandwidth. But if we increase, for example, this bit into 16, will the bandwidth will be higher, or bandwidth requirement will be higher or lower? If we increase the number of bits per second?
Higher.
It is very simple, okay? If we increase, for in 1 second, you are sending 8 bits. Now you are 16 bits. If we use pulse to send the bits, then pulse width will be nearly halved. If your pulse width is halved, then in order to process this pulse, you need your system bandwidth that must be double of the that what have you used for 8 bit. For this reason, actually, when we are sending data over cable or many other systems to process that digital data, that we need not a single system or a media can handle all data rate. You need, for example, higher data rate, you need what do you call higher bandwidth, and that bandwidth concepts come from this simple example, okay? If we change the width of our pulse, for shorter pulse, longer bandwidth will be needed. And shorter pulse signifies that we are sending more pulse in a certain time period. So this is one example of our time domain, that we have a pulse, continuous pulse in the time domain. The corresponding frequency domain or Fourier transform is a sinc function, something like this. Now let us go in the reverse way, that if we have a frequency spectrum, xj omega, that xj omega has this form. It is something like this, okay? W to W, this is your omega. That means if we have a spectrum, it can have a magnitude equal to 1 or other value that will not change the time profile of your signal. Then we need to know what will be the corresponding xt. Then that result will be very useful for us to find the Fourier transform or handle our signals very easily later. Okay, in order to find xt, what you need to do, you take the Fourier inverse of your signal. Then we know that xt will be equal to what? 1 divided by twice pi integration, although it is from minus infinity to infinity, but in our case, we do not have our xj omega in other region, minus w to w of your xj omega. It is real and amplitude equal to 1. Then e to the power j omega t. We have to integrate it over. Am I connected or disconnected?
So now you are connected.
Okay, d omega. So we have to evaluate that integral. Anybody can evaluate that integral. You will see the result in the next slide. But you see that this signifies that you can easily identify that the corresponding time domain signal will be a sinc function. Okay, here you are. So this is what our result, okay? You can find the value at t equal to 0, it will be equal to w divided by pi, and other values will be something like this. By changing the variable, you can easily convert it into sinc function. Then your signal will be equal to what? Your signal will be something like this, isn't it? And this value would be equal to what? W divided by pi, and this axis is time. So we have a signal something like this in the frequency domain, omega. Then corresponding time domain signal is a sinc function. We have a signal, for example, a pulse in the time domain, and the corresponding xj omega is also a sinc function, isn't it? And this is the duality property of Fourier transform, okay, that we need to remember, because we will use this duality property later when we will be illustrating few application examples. Okay, with this thing, another thing we need to know regarding the behavior of the impulse, that already we have investigated for the case of discrete time, and we have to investigate the thing for continuous time also. That means if we have an impulse, the localized signal in the time domain, okay, here you see that we have a signal, say this is our time, and this is your signal delta t. Then what will be the Fourier transform of this signal? Just simply apply your signal there in the Fourier transform equation. By using shifting property, you see that this integral value equal to what? This is the value of this function at time t equal to 0, because your signal is appearing at t equal to 0. So it will be equal to simply e to the power minus j omega dot 0 is equal to 1. What does it mean then? It means that if we have a Fourier time domain localized signal in the form of an impulse at t equal to 0, that will contain, for example, the frequency from minus infinity to infinity, the Fourier transform would be equal to 1. If we add an strength there, that strength will again be coming into the Fourier transform as a multiplication factor. So this is very important, and you know this behavior from your Laplace transform also. In the Laplace transform, you have all seen that for Laplace transform, the Laplace transform of an impulse is equal to what? Is it not equal to 1? Okay, now let us extend this thing a bit further. If we extend this thing in further, then what you can do, you can just shift your signal to somewhere, okay? If we shift, for example, delta, if we shift our delta, so this is our delta, and let us consider that this delta is shifted here. Delta say t minus t0. Let us shift the delta to t minus t0. Then what will be the corresponding Fourier transform? Can you guess? Because in this case, your Fourier transform would be equal to what? Integration minus infinity to infinity delta t minus t0 e to the power j omega t dt. What is the value?
So e to the power j omega t naught.
Minus is there, actually I have made a mistake. It is equal to
E to the power minus j omega t naught.
yes, because this is simply equal to the value of your function. This is simply equal to the value of your function at omega t equal to t0, and it will be equal to e to the power j omega t0, isn't it?
Yes, sir.
Okay, so this is very similar to what we have seen in the case of what we call discrete time case. Okay, the shifting usually results in a phase shift factor, and that is simply e to the power plus minus j omega t0. If you shift is occurring in the reverse direction, negative side, then it will be plus. Okay, this will be needed to find the Fourier transform of a function that is shifted from one location to another. Okay, now let us consider okay, this equation, you see it is bidirectional. That means forward transformation is associated with the inverse. So if we have a signal, that signal is localized in the time domain, but it will not be localized in the frequency domain. It will have a constant DC-like structure in the frequency domain. Now, if we want to bring a signal back, okay, some intuitive thing can also be applied there in order to find the inverse Fourier transform. Can you tell me that if we have a DC signal that is existing from minus infinity to infinity, if we want to find the frequency of that signal, what will be the frequency for a DC signal?
So DC signal has no frequency, sir.
DC signal had no frequency. So your corresponding signal will be equal to what? That means we have, if we have a DC signal, no frequencies are there, then you see that that DC signal will have a frequency spectrum that is occurring at omega equal to 0, isn't it? If this is your omega, then we will have a delta of omega there for a DC signal. That is the thing that we can say by simple intuition. Okay, that can be verified here. Okay, consider that we have a delta in the frequency domain, and it is multiplied or scale or an strength is there twice by say. Then if we consider that this is what our signal in the frequency domain, that means it is a localized signal in the frequency domain occurring at omega equal to omega equal to 0. And this integral is the inverse Fourier transform, and that is to be integrated with respect to omega. Then what will be the value of that integral? Because your function here, that is apart from your delta omega, we have a function there e to the power j omega t that you are multiplying with delta omega and integrating over omega. Then is that integral is the value of e to the power j omega t at omega equal to 0, isn't it?
Yes, sir.
So that is there, then it will be equal to 1 divided by twice pi. You have your twice pi there, value of your e to the power j 0 t is equal to 1. So we are getting a DC signal, okay, with amplitude equal to 1. If twice pi is not there, then a twice pi factor will be there, okay, 1 divided by twice pi, that's it. So then what can we conclude then? If we have a DC, then the corresponding spectrum will be an impulse in the frequency domain, isn't it? And if we have an impulse in the time domain, then we will have what? A DC like signal in the frequency domain. That duality is needed to take the Fourier inverse. Okay, at this stage, I will be illustrating one shifting property in the frequency domain that will be needed to take the Fourier transform or Fourier inverse of some representative functions. Okay. Let us consider, because we have illustrated two things, that if your time domain impulse is at t equal to 0, what is its transform? If it is shifted, then what is its transform? Now we let us investigate the shift property in the frequency domain. Consider that we have initially we considered our delta twice by delta omega for this example. Now consider that we are shifting this delta in the frequency domain by a frequency at omega 0. Then this will be equal to twice pi delta omega minus omega 0, isn't it?
Yes, sir.
Then what will be the Fourier inverse corresponding signal xt? Your xt can be calculated in this way. Xt will be equal to 1 by twice pi integration minus infinity to infinity. It will be equal to twice pi delta omega minus omega 0 e to the power j omega t t omega. What is the value? E to the power j omega 0 t, isn't it?
Yes, sir.
Similarly, if we have a shift in the reverse direction, say we are shifting here with minus omega 0, your signal will be twice pi delta omega plus omega 0, then corresponding term will be equal to Fourier transform will be equal to what? E to the power minus j omega 0 t, isn't it?
Yes, sir.
Okay, fine. Then with this result, can you find the Fourier transform of a function xt equal to cos omega 0 t?
Yes, sir.
How?
So Euler's identity.
You just use Euler's identity. It would be, this would be equal to half e to the power minus j omega 0 t plus e to the power j omega 0 t, isn't it? From this equation, we know that Fourier transform of e to the power, if you want to find Fourier transform of e to the power, that is Fourier transform or Fourier inverse, not transform, Fourier inverse of, what do you call, Fourier inverse of this quantity is equal to e to the power plus j omega t, and Fourier transform of plus j omega t equal to e to the power minus j omega t. Then you can readily write that this will be equal to twice pi for Fourier transform of xt equal to what then? Half into what? Half into twice pi. For your minus term, it will be equal to plus delta omega plus omega 0. And for the second term, it will be equal to twice pi delta omega minus omega 0, isn't it?
Yes, sir.
This will be the Fourier transform of your cos omega 0, and that can be easily justified actually. You see that this signal is actually a periodic signal, is it not periodic?
Yes, sir.
It is a periodic signal, and frequency equal to omega 0. It cannot have any other frequency in it. Does it contain any
Yes,
other
sir.
frequency in it?
No,
That
sir.
means it has a frequency equal to omega 0. And as we are using complex form of Fourier transform, for this reason, we will be getting two impulses of there in frequency domain. One will be appearing at omega 0, another will be appearing at minus omega 0, just to make the signal real. Okay, so this is very simple to be understood. So if you want to plot the Fourier transform of this quantity, then it will be equal to, at omega equal to omega 0, this is what this thing. At omega equal to minus omega 0, this is what this thing. You got my point? And
Yes,
the
sir.
amplitude or the associated scaling factor will be pi. This is pi delta omega minus omega 0. This will be equal to pi delta omega plus omega 0. So in this way, you can easily find, and this is impulse. Be careful about that. In frequency domain, the amplitude is tending to infinity, because this thing cannot be used directly. Okay, this is coming from, actually we do not need to take the Fourier transform or Fourier series of cosine omega 0 t, because the frequency information is always with us. This is a simple illustration of the thing, that if we have a signal that must be combined with this type of signal, in this case later we will see some properties that some multiplication and convolution properties are also there that will be important. In this case, this will be needed. Now
Yes, sir.
I will be discussing few other practical examples that how Fourier transform help us to investigate many of the things that actually we cannot identify by using simple time domain form. Then I will conclude my lecture today. We will be going to what we call whiteboard for this illustration. Okay, consider that we have a system. Okay, in our chapter 2, we have some discrete time system. One of subsystem was moving average type. Moving average type actually take the consecutive samples of a digital discrete times signal, then average it, because this is actually a filtering operation is actually done by averaging. That cannot be actually visualized so easily in the time domain, but you will see that in the frequency domain, you will see that a moving average system is actually some sort of filtering. That I will be illustrating here. It is there also in your book, but let me again redo it just to know some anterior detail of it. Okay, consider a 2-point moving average system. It is equal to half. We are taking 2 consecutive samples, xn and x minus 1, to find the output. This is a simple moving average system. You see that how it will smooth your system. Okay, consider that we have a signal here x, another signal here y, another x is there, something like this. Okay, this is your x0, this is your x1, this is your x2. If we put this into this moving average system, our y1 would be equal to what? Your y1 would be equal to half into x0 plus x1 plus x0, isn't it? The if, for example, this is 1, this is 2, say this is 1.5, something like this, then your x1 would be equal, y1 would be equal to what? Okay, you try to investigate by your own. You will see that this will give you a more smoother figure in x. That can be understood in frequency domain so easily. Okay, how can we do that? You simply extract the transfer function, then you investigate the transfer function. That will tell you that whether what type of filtering action is being done there. In order to find the impulse response, what you need to do, you replace your input by the impulse. That means our impulse response hn would be equal to what? Hn would be equal to half delta n. The input is delta plus delta n minus 1. This is what your impulse response in time domain.
Yes, sir.
If we transfer it into frequency domain, then this will be equal to H j omega. In this case, our system is discrete time. So it will be equal to, we usually express our discrete time transform as H into function of e to the power j capital omega. That will be equal to what? This is the Fourier transform of this term and Fourier transform of this term. What will be the Fourier transform of this term? It will be equal to simply half into 1. And due to the shift, we are getting what? A factor will be there, e to the power minus j omega, because one sample is shifted, isn't it?
Yes, sir.
Something like this. Then can we express it into into a form that will contain, for example, our or you can easily find the magnitude as well as the phase angle of your spectrum and investigate that how your magnitude is changing with omega. That will tell you what filtering action is being done there. Okay. So your H e to the power j omega will be equal to half into 1 plus e to the power minus j capital omega. By use your Euler identity there, that 1 can be replaced by minus j omega by 2 into e to the power j omega by 2. Can't you do that? Plus this can be written as omega by 2 into e to the power minus j omega by 2, isn't it?
Yes, sir. Yes.
Then you can take e to the power minus j omega by 2 as a common factor. Then it will be equal to what? E to the power j omega by 2 plus e to the power minus j omega by 2. That is equal to what? It is simply cosine. A 2 is there, 2 can be there. Okay, it is simply cosine omega by 2, isn't
Yes,
it?
sir.
So this equation is simply e to the power minus j omega by 2 into cosine omega by 2, isn't it? So how the magnitude is changing then? You see that the magnitude of H e to the power j omega is equal to simply magnitude of cosine pi by 2 capital omega by 2, isn't it? Because magnitude of exponential term complex with complex argument equal to 1.
Yes, sir.
So if we want to plot it in frequency domain, how it will look like at omega equal to 0, the value is equal to 1. Then in other case, at omega equal to pi, value equal to what? 0. Isn't it?
Yes, sir.
Then it will take this shape. And again, if we go into the next cycle, it will take this shape. But we need to investigate from minus pi to pi. Okay, what type of filtering action is being done by this filter? What type of filtering? Just by examining from minus pi to pi?
So band pass,
What band is passing?
low pass filter.
Okay, try to investigate the thing, what type of filtering action is being done there. Okay, some other examples are also there in your book. Try to know about it. Okay, but apart from this thing, the main what we call benchmark equations that we usually use, we have to explore some properties of Fourier transform that will help us to determine the Fourier inverse or Fourier transform easily. The reason is that not always you can perform the integral, that will consume time. Like Laplace transform, we usually what we do, we usually take help of some properties to find the Fourier transform or Laplace transform so easily. For this reason, we have to investigate few properties of our Fourier transform. Okay, usually Fourier and Laplace transform are all applicable generally for linear system. Linearity property will be applicable all linearity property will be applicable for Fourier transform and Fourier series. Okay, if we go with our continuous time, you see that if we have a periodic signal, say xt and yt, both xt and yt can be expressed in Fourier series. We can prepare a signal zt that is a linear combination of xt and yt. Then we need not to determine the Fourier series of constants for xt. If we know the Fourier constant of xt and yt, they will be related in the same way as they are related in the time domain. For example, something like this. If xj omega is the Fourier transform, or this Fourier transform, actually it must go in the reverse way. This should be discussed first. Okay, this is your Fourier series. So your Fourier constant, you need not to determine the Fourier constant. Just 1 second. Okay. So in your Fourier series, you see if xk is the Fourier series constant of xt and yk is for yt, then you zk, the Fourier constant of the resulting signal that is obtained from linear combination of xt and yt, is simple a linear combination of xk and yk. Same is true for Fourier transform and for both your discrete time and continuous time case. We'll illustrate the thing, for example, say using this example. Okay, this is a periodic signal, isn't it? Is it periodic or non-periodic?
Periodic.
Periodic. It is a periodic signal. If it is periodic, it is continuous time. So your signal is there. You can directly handle this signal to find your Fourier constant. But if we can split our signal into more simpler form, then it will help you to find the Fourier constant easily by simply applying the result that you obtain for some representative periodic signals. You see that this is somewhat like a square wave. But if we decompose this signal, we will find two square waves there. They are superimposed, and we can get our zt. And that equation is this. Okay, if we add, for example, these two figures together with this factor 3/2.5, you will get your original signal xt. So whenever a signal is given, by splitting the signal into a simpler constituent, then say we have this signal with us. Okay, in many of our earlier instances, we have already determined the Fourier constant xk for this type of signal. Then this same equation can be used there to find our xk and find yk. Once your xk and yk are available, you need not to find the Fourier constant of zk. Simply your zk would be equal to what? Would be equal to 3 divided by 2 into xk plus half into yk. That this will be the Fourier series of constants or coefficients of the exponential form of Fourier series of the signal zk. So this property can be applied in many of our purposes. These are the simple methods, okay, or some techniques that will facilitate in doing or performing the calculation of Fourier constants. Okay, this example is already illustrated there by using the previously calculated result. We have some other properties as our time already elapsed. So I will be ending my lecture today at this point. We will be starting from table 3.4 in the next class, inshallah. And your class test will be on the 14th at 2 p.m. using IUT LMS. Okay, in the next class, I will make some changes there because I have having some physical issues because constantly sitting and in a chair, creating my health problem. So probably I will be taking some rest in the next cycle by merging two sections together. It's very difficult. Even I cannot sleep. I have to be on a screen from 8 p.m. to around 11 p.m. Your section
Section B, sir.
35, 1635.
Present, sir.